If you're a fan of science fiction or just really keen for humans to find alien life, you might have heard of the Drake equation. It was coined in 1961 by astronomer Frank Drake, and it provides an estimate for how many advanced alien civilizations there could be in our galaxy. But I hate to break it to you, 1961 was over 60 years ago, and 3 decades before we discovered any planets beyond our solar system. In all that time, astronomers have been able to learn a lot more about how the universe ticks, how abundant the ingredients of life are, and what conditions may or may not be necessary to give rise to life. So the question we have here at SciShow is this: is there any value in going back to that equation, or should we come up with something entirely brand new? For everyone who doesn't have the original Drake equation etched into their memory, including me, it looks like this. In some versions, the multiplication signs aren't there, but remember, that's really the only kind of math this formula makes you do. And I know that's a lot of letters, but I am here to walk you through them. N is the number of alien civilizations that live in a given galaxy, and that given galaxy is almost always ours, the Milky Way. For the terms on the right side of that equal sign, you can think of each as belonging to one of 3 groups: astronomical, biological, and social. Our star is the formation rate of stars in a galaxy. How many stars form every year, on average? F sub p is the fraction of stars in that galaxy that have planets. N sub e is the average number of planets per solar system that are potentially habitable. F sub l is the fraction of habitable planets that actually develop life. F sub I is the fraction of those inhabited planets that manage to develop life where that life is intelligent. And then F sub c is the fraction of those planets where intelligent life has developed technology we can detect from Earth. And finally, L is the average time that technology is going to be broadcasting into space. Not how long the civilization has been around, just how long they've been able to talk with the universe. Like, even though anatomical humans have been around for a couple 100,000 years, give or take, our radio signals have been leaking into space for a lot closer to like a single century. And now you might be screaming, why does this even matter? It's not like this shows us where the rest of those N civilizations are, or puts us into contact with them, or anything. Well, technically, the Drake equation was always more of a conversation starter than a truly helpful equation, which I say with all the love in the world. Frank Drake created it to help organize a radio astronomy conference. It was a way to get astronomers thinking about what things they'd need to know to answer the question, how many aliens are out there? And at the time, only our star had any kind of estimated value. But now we've got a little more to go on. And over the decades, astronomers have learned enough to start debating whether the Drake equation needs a makeover or just needs to retire. One revision from 2013 proposed simplifying the entire Drake equation to just this. Well, simplifying in terms of aesthetics, at least. This version basically recognizes those 3 groups I mentioned before, but also smooshes most of the biological and social stuff together. It's not really less complex. In fact, when you peer under the hood, it's probably even more complex because of how complicated the universe turned out to be. First, we'll take a look at what's hiding in that deceptively simple R sub astro term. Over the past 6 decades, astronomers have learned just how not constant the original R star term is, because it turns out that a galaxy's star formation rate evolves over time, and when it comes to hosting planets, not all stars are created equal. Different kinds of stars are better or worse at forming different kinds of planets, especially habitable planets. For example, red dwarfs can go through a stellar version of the terrible twos that strips planets up their atmosphere. Meanwhile, stars that are similar in mass to our sun evolve pretty fast, and shorter lifespans mean shorter amounts of time that a planet can host life. So according to many astronomers, it's actually the stars in between red dwarfs and our sun, called K-stars, that are the best bet for habitable planets. But even 3 decades in, we're still in the early days for exoplanet research. Astronomers have identified like 30 rocky worlds that could maybe hypothetically host life as we know it. And our search for these worlds is still very biased, but not towards our own setup, like trying to find Earth 2.0 around Sun 2.0. It's actually biased towards finding planetary systems where the planets orbit really close to their stars, just because it's a lot easier to see those planets. So we're still working out how many planets we're really dealing with out there, even before considering the lack of nuance brought to you by the habitable zone. What's that, you ask? A habitable zone attempts to predict where a planet could orbit a given star and maintain liquid water on its surface, because liquid water is a critical ingredient for life as we know it. But a planet just being in the habitable zone doesn't mean it's actually habitable. For example, red dwarfs are small and dim, so their habitable zones are super close. Not only close enough for a planet to get its atmosphere stripped away, but close enough for the star's gravity to sometimes lock the planet into place, one half in perpetual day and the other half in perpetual night. In contrast, just because a planet isn't in its star's habitable zone doesn't mean it's uninhabitable. For one thing, a star's habitable zone actually migrates as it ages. So when life first arose on Earth, like 3.8-ish billion years ago, our planet wasn't inside the sun's habitable zone. Supposedly, it was too far out, and any liquid surface water should have been a bunch of ice. But Earth had a thick atmosphere full of greenhouse gases that kept it warm. Then there's the fact that planets are not the only worlds that could potentially host life. They may not have appeared in any part of Drake's original equation, but any good conversation about habitable worlds these days is eventually going to turn to moons. Moons like Europa, which thanks to its gravitational interaction with Jupiter and its lunar siblings, has a salty ocean buried underneath kilometers of ice. And get this, the Europa Clipper mission, which is set to launch in October 2024, has a little silver plate engraved with, among other things, the original Drake equation. So it's clear that some NASA nerds still hold it in their hearts, even if other astronomers want to rework it. And with that rework have come attempts to actually calculate r sub astro, or similar terms. For example, that 2013 paper estimates that one habitable planet forms in our galaxy just every 10 years. But that's really just a starting point for whatever the rest of the equation looks like. So let's move on to F sub biotech, which smooshes together all the terms from the original Drake equation that deal with life actually evolving on potentially habitable worlds, and also evolving enough to produce signals we can detect. Unfortunately, here's where we run into a bit of a wall. Astronomers can try to use Earth as a proxy, but we don't actually know how easy it is for a planet to produce life, let alone intelligent life, because we only know of one place where it happened. And everywhere else, we've only found the ingredients for life, like water, carbon, and nitrogen. Although, to be fair, certain ingredients seem to be, like, everywhere. We found them on moons, on asteroids. There was even a couple complex organic molecules found floating loose in protoplanetary disks, but this is all a very far cry from life itself. That being said, the Drake equation and its reworked successor don't seem to be accounting for everything they might need to. Like, what about aliens colonizing uninhabited planets? Or what if some aliens are populating planets with robotic probes that can send signals implying that there's life on that planet, even though there isn't? Or what if an alien civilization got wiped out, but the technology it left behind kept transmitting? Are we gonna have to argue about alien AI before we even figure out what constitutes AI down here? Well, maybe. One paper from 2020 used the Drake equation to estimate the number of potential artificial civilizations in the galaxy, and then compare that to the number of potential biological civilizations that the original Drake equation was focused on. AI civilizations often wound up outnumbering the biological ones, so our search for life may actually be more likely to turn up super incredibly intelligent computers, which is a really wild concept, and also a very creative use of the Drake equation. But again, not really what Drake had in mind with the original. All those non-straightforward civilization establishing considerations are pretty new, and those are some pretty big holes to fill in order to really feel like we've covered all of our extraterrestrial bases. But maybe that's more than you really need. If you think the 2013 version is as simple as it gets, Drake himself is about to rock your world. The most important term in this equation is time, which Drake believed so much that he had a license plate that literally read n equals L. And here's the thing, we don't have to limit our search to the kind of proverbial yelling that Drake originally had. The original formula was focused on aliens sending radio signals out into the universe, but we can try to hunt for other signs of alien civilizations, or we can focus on biosignatures that may tell us whether there's any life on a planet, like at all. Now that we have more flexible and sensitive tech, we're not limited to only listening for the loudest signals of extraterrestrial life. For example, we can see if a planet has a significant amount of oxygen gas in its atmosphere. Maybe that's an alien form of photosynthesis. And compared to a century of radio waves, life has been pumping oxygen into Earth's atmosphere for like 2 billion years. In other words, we're not just chopping off some of those later terms based on intelligent life evolving and developing. We're jacking up the values we can plug in for L. And ultimately, a biosignature-based Drake equation requires a different kind of rewrite than just smushing together some terms. We have to reconceptualize what's important. Will we really only be satisfied once we find an alien that can tell us to live long and prosper? Or given how much our tech has progressed since Star Trek went on the air, maybe we lean into finding any definitive signs that life exists beyond this tiny blue dot floating through the cosmos. We can still etch the original Drake equation into our spacecraft plates, though. It'd be a solid conversation starter for any aliens that want to hear the story of how we eventually found them. And if I had my way, I'd sneak into whatever factory they're making those plates in and carve a thank you to our patrons, because I want the aliens to know how much your support means to us as well. You're awesome. Thanks for watching.